Good morning, everyone. I'm happy to be here in this PyTech Summit edition to represent Unit 8. I'm Eliane Maalouf. I'm a data scientist at Unit 8, and today I will be presenting DARTS, a one-stop shop for time series forecasting and analysis. So why do we care about time series forecasting in the first place? Well, actually, time series forecasting is related to many decision-making problems in different contexts. So let's take a few examples. Think about a retail store, for example. They need to understand the need of the consumers and their demand for a certain type of product or products in order to buy the right amount without waste and overspending. Or imagine, for example, in the energy context, you might, like an energy company does not have a way currently to efficiently store energy, so they need to, of course, plan the demand and plan their capability to produce energy. Or in the context, for example, of telecommunications, you need to plan your infrastructure such that it is stable and it is able to accommodate for peak times. And in these different contexts, actually, there's a common underlying way of understanding these problems, which is through what we call the time series data. Time series data is usually a value that is varying in time. So you have this value that is being measured at different moments in time. And you want to take this time series data and use it in order to say something about the future of this value. And ideally, you would like also to have some form of uncertainty quantification about the prediction you're making with a model that is helping you to forecast. So forecasting is usually the goal of forecasting is usually to create actually a model that we call here in this slide f, a function f. That's the history of the value that you, the measurement of the value that you have. So the history of your time series with some additional data. And the goal of this model is to give you some prediction of the future. Of course, behind all this, there is the assumption that there is some signal in the data that can be captured by the function of the model. So the DARTS library aims to help you in this process of creating the model and analyzing the time series. So maybe a few important points about DARTS. It's an open source Python library. And its aim is to be user-friendly and also provide support for most modern machine learning models. Its main object is this time series object, which is basically the building block to collect the data and to transform the data to prepare them for the model. A second important point is that it aims to have a unified fit and predict interfaces for all the models that are implemented. It has a very wide range of models that are integrated, ranging from the classical models, from statistics and econometrics, to most of the current state-of-the-art machine learning approaches. And really, one focus point that is always in front of DARTS developers is the user friendliness. So the goal is always to have a very intuitive API for the user with some reasonable defaults on the parameters. So maybe to show you the large ecosystem of DARTS, the goal, of course, is to have a good modeling library for time series, but it doesn't only provide that. It also provides supporting tools around the modeling part. So it helps you in the process of discovering the time series from statistical analysis and visualizations, but also it helps you in pre-processing. There are multiple types of transformers that would help you, for example, in filling missing values in the time series, in normalizing the data, or even extracting some trend and seasonality from the data. Then, of course, there is this modeling part that we're going to discuss a bit about, which has the models, but also has different ways of combining models or combining time series in order to improve the modeling part. And then, in support of all this, there is this evaluation. There's this evaluation group of elements, which basically provides metrics, but also optimization tools and analysis tools of the predictions that were done by the models. So that's maybe a bit of history about this library. It started as an internal project first, and then it was publicly released as open source library on GitHub in 2020. We are currently at version 0.22, and in a couple of weeks we'll be already at 0.23. And really, since its public release until now, it has gotten a lot of attention and a lot of traction. We have contributors both from inside the Unit8 and from the outside. So it's there are more than 60 contributors contributing to this library very, very actively. So let's see how it works, and maybe on a simple example. Let's say you have this time series that you want to try to forecast. And you have this black part, which is your training, and you want to predict and compare to the blue part, which is the validation part. And ideally, you want your predictions, which would be the red lines here, to be as close as possible to the reality. So you imagine you have a good model that will give you good predictions in this, hopefully, let's say, at the end of the analysis. So the entry point into darts is this time series object. The idea from this object is that you instantiate a time series from a file. For example, you can read from a CSV, but you can also import your data from another data frame, from NumPy array in general. So there are different functionalities to import data inside darts. Once you have this object created, then you can start by preparing the data. For example, you want to split your data to train and validation. There is a functionality for that, which is a method of the time series. You can call, for example, split after, and the proportion the proportion of training that you want. In this case, for example, I'm asking it to give me 80% for the training and 20% for the split. You can also split on a specific time index, and it will adapt your time series split for that. Now, let's say you want to start modeling and you are testing with some baseline models. Let's take the exponential smoothing one. The exponential smoothing one, for example, is a class inside darts. The important thing is to import it and create an instance of this model. And then you can just call the fit on the training, and you can call the predict and tell the predict function how long in the future you want to predict. If you want to test another model, say the model theta, then it's the same idea. You import the model theta, you create an instance, and then you call in the same way, exactly the same way, fit and predict in order to do the same predictions. I'll not be going into details into the modeling and the specificities of each of that type of model. What's important for me to show you here is that whatever model you want to use, you will just instantiate the model and then call the same fit and predict functions. Now, say you want to compare these two models, then you will have to import also, which are implemented in Dart, some metrics of comparison, which are adapted to time series forecasting. Let's say you have chosen to use the mean absolute percentage error, which is one very common in this context. In this case, for example, you might choose the theta model because it has a lower mapping. But of course, if you are testing multiple models, probably at some point you will start be overfitting on the specific split that you have done in your data set. So we provide also, Darts provides also an important functionality, which is historical forecast and backtest, which depends on historical forecast. But the idea of these two functions basically is to simulate how the model would have performed if it had been historically used to forecast the time series. So you can think about this function basically as adapting cross-validation into the context of time series forecasting. And historical forecast, what it does basically, it will train the model multiple times, but every time it will change the split in the data. You can actually manage this function with different parameterization. For example, you can decide if you want your training to be increasing or if you want it to be fixed. But the basic idea behind it is that the model will be trained a first time on a first split, and then the training will be extended with a stride, and the model will be trained again and revalidated on the validation set. And this process will go on as much as needed in order to cover the whole series. And so the output of the historical forecast is basically a list of predictions at these different steps. Of course, this is a lot of information. So backtesting is a convenience method, let's say, that combines this historical forecast predictions with a metric that would, in some sense, summarize the quality of the predictions that you had at each step. And then you can use these estimations of the metric in order to let's say, do some analysis on the quality of your model. But then you might also, for example, start by selecting a specific family of models that you want to work with. You can optimize its hyperparameters, for example, based on the data that you have. There is a functionality of grid search inside DARTS. The idea behind it is that you provide the different ranges of values that you want to test for the different parameters. And the grid search, which is a class method, you will call it on the class of the model. For example, if you're working with the model theta, you will call it on the class theta. And what it does in the background, it will actually take all the combinations of the different parameters that you have provided and train models and do actually the backtesting that we have seen before. And at the end, it will give you the best model. It will give you an instance actually of the model with the best parameters. You still have to fit this model with the training set and validate it on the validation set. So let's say, for example, here in this situation, maybe the model have tested these different parameters that we have seen before. And in the theta method, for example, you can choose different types of seasonality, and you have the theta parameter that you can choose. For this data set, it seems that the model with the seasonality of type additive, so this seasonality mode, and this theta parameter of 2.5 was more adapted to this data set. So this was the one that was selected by grid search, for example. You might also care about combining different models. Say, for example, you have these two not necessarily perfect models that you have trained before, the theta and the exponential smoothing one. And the idea behind ensembling is that you would like to see if there's a possibility to combine the predictions of these two models to get an ensemble that is better than each one of them separately. And there is actually also in DARTS a possibility to combine models. There is an ensemble model class. The idea of it is that it will take a list of the models that you want to ensemble together, and you can choose how you want to ensemble them. So in this example here on the slide, I'm saying that I want to ensemble them using a regression model. You can use any regression model that is available in scikit-learn, for example. And the idea of this regression model, which is ensembling the predictions of both theta and exponential smoothing, is that it will learn the parameters from the predictions of theta and exponential smoothing, such that we have the parameters that best would give the best combination of predictions that is close to the validation set. So you can imagine basically here that again, you can use the ensemble model like any other model in DARTS. You can call it with a fit, and then you can use it at prediction time with predict. And at prediction time, basically what it's doing, it's calling the prediction on theta, it's calling the prediction on an exponential smoothing, and it's using the parameters that were learned before in order to combine these two predictions together. So it's a way also, there are two types of actually of ensembling in DARTS. There is a naive ensemble and there is a regression based ensemble. Maybe an important word about some of the features in DARTS. I will start speaking about covariates. Covariates is how you integrate information from external data. So in DARTS, we usually speak about three types of time series. The main time series that we care about predicting, which is what we call the target series. But there are two other types of time series that could be used could be used as features, let's say, in the models. The first one is the past covariate, which is basically a time series for which values we have observed until the forecast time. So its values are only in the past. We don't have them in the future the horizon that we want to predict on. And this, for example, could be measurements of some quantity that is related to the quantity we care about. And you have also the possibility to integrate future covariates, which are still time series, for which we might have values in the past, but the important bit is that we need to have them also in the future. So basically in the future horizon on which we want to predict. So this could be a calendar information. We know, for example, in the future when holidays will take place, but they could be forecast from other sources. It could be, for example, some forecast of the weather. So this is an information we might have about the future. And of course, so the idea behind these two is that you can integrate them, the past and the future covariates, as part of the fit function. So they can be used as features in the models. And if you provide a future covariate, as I mentioned, you need to also provide its future values during prediction time. And the important bit is that also the user does not need to align these two time series with the target time series. It's being done by the library itself, which aligns the series as needed. An important part also about feature generation, automatic feature generation this time, is the encoder. So there is a possibility with darts actually to ask darts to generate from the time index some extra features. So these we call them encoders. Basically, they can generate past and or future covariates for you from the time index of the time series. So from the time index, it means that they will encode information that is in the time index that you have about, for example, day of the week, which month it is. They might encode also some the same information, but in a cyclic way. So by using trigonometric, by transforming this time index with trigonometric functions. But the user also can provide some custom user-defined functions in order to transform this time index specifically. So these are, let's say, a very cheap way of generating new features for the models. I will speak a bit about the support for multivariate series and multiple series. So we call multivariate series as compared to univariate series. So let me start with univariate time series. A univariate time series is just one value that is changing over time. A multivariate series would be a vector of values, so multiple values that are changing together over time. And we call them, in this context, we're calling them components or dimensions, let's say. And the important thing is that these components are sharing the same time index. For the user, this is invisible because the user will only create them in the same time series object. And the user will just give them to the model in the same way. And the idea behind that is that you can imagine these multivariate time series as different univariate series that are combined together. So you can also ask the model to predict for each. So the model will be able to predict for each component in one go. Currently, all machine learning models, for example, support multivariate time series. And I think already in the next version, all models, also the baseline models, will support multivariate series. Then what is the multiple time series? Here you can imagine that you have different series. They could be each multivariate or univariate, and you want to provide them all together to the model. And actually, they are given to the model with a sequence, with a list. And this is very interesting because you can fit, for example, the model. This is supported in the machine learning models. You can give a list of series to fit the model, and then you can call the predict on one of those series or on another series that was not used inside the training set. So this basically prepares us to the next important, let's say, feature or capability of DARTS, which is supporting global forecasting. Global forecasting is this idea of providing multiple time series for training, and then using this model that was trained on many more time series than you usually do in the classical way, and then use it on forecasting maybe a new series that was not in the training, and actually adapting very quickly to the new time series. So The models that are in DARS that support this are all regression models that come from scikit-learn, for example. We provide a wrapper that wraps around any regressors that comes from scikit-learn, but also LightGBM and CatBoost. And for these models specifically, so since they take table data, there is a step that is done before, but also here the user doesn't do it by hand, but maybe it's just interesting to show it. This step is the step of transforming the series, from a list of values into a table of values by providing lags. For example, here the user would create would like to create a model with 2 lags. So the idea of creating this table is that at each value of the time series, the model will correlate it with 2 values of the same time series from the past. And part of this will be the training, of course. And the idea behind this is that since it's a scikit-learn regressor, for example, or a LightGBM or CatBoost, they will just ingest the data in the same way as they use for any type of regression, whether it's time series or not. And the data will be represented as features in the matrix X and as labels in the vector Y. Once the model is trained, basically the same process works in order to create new features from the end of the time series in order to predict the next step and the next step after that. So as I mentioned, the user does not have to worry about that. They only need to create the instance of the regression model they care about and specify the lag that they wish to use. So of course here there is the lag of the target series. If they are using past covariate or future covariates, they also can specify different lags for the future covariate and the past covariate. So then how do these models predict as a regression models? We have that's combined two methods of prediction. So once you create the model, let's check a bit here on this this model creation. You have a parameter which is called output chunk length equals 2. This output chunk length basically tells the model when it's being created how far into the future it needs to predict out of the box. Basically, in one go, it needs to predict 2 steps into the future. Currently, in the current implementation, this means that the model will create 2 models, one for each step in the future it needs to predict on. But then this does not mean that you cannot predict for longer. When you call the predict function, you can define a horizon, a prediction horizon, which is larger, which is longer than the output chunk length. In that sense, what happens is this autoregressive part. So you have these 2 models, model 1 and model 2, that were used, that were trained by the regression model, for example. Then if you want to predict for a horizon that is longer than 2, these 2 predictions that were done at the previous step will be used autoregressively as new features for the next steps. So there are these 2 modes. Basically, the advantage of this is that we don't accumulate the error for too long if we are doing just autoregressive steps with output chunk length 1, and we don't create many models as if we were only doing the direct part. And of course, in the regression models, we have rich support for deep learning models. I will not go into details about each of those models, but there's support for sequence models like the RNN ones, for temporal convolutional models like the TCN one here, more modern transformer models, transformer model and TFT model, for example, and some that are based on residuals, residual blocks like the NBits and the NHITs, which are quite also used in time series forecasting. The important bit to realize here is that we are always trying to integrate new models, of course, when it makes sense and when the models seem to be relevant and basically of good quality, let's say, from the research papers that we read. Maybe the interesting part that was done for these models is how actually they ingest data and many of their, let's say, of their common processes for training and data preparation are all abstracted away. So this, for example, helps us to integrate new models, but also helps the community to integrate new models very, very fast. The idea behind it is that any new model, let's say the model here in the middle, would only expect to receive some pre-formatted input chunk length. So this is the length of the input that the model needs to see in the past in order to prepare the prediction. And this is a combination of the different covariates and the target series, of course. And then the model needs only to output this output chunk length, which is the horizon at which it needs to predict in the future for the target series only. So by standardizing this let's say this structure of input output in this way, the model inside does not need to worry how to construct this input output. So in order to do that, the creators of DARTS created also a training dataset class, basically that abstracts all this data preparation for the user. So it takes actually the input sequence of the time series and it cuts the time series into subsequences of input output for the supervised models, and it does the same thing for all the series inside this sequence. So, but of course, this training data set could be changed depending on the need of the user. So if the user needs some other form of data preparation, they can adapt this class for their model or for their need. Maybe a word about the ability of these models to scale with DARTS specifically. Here, it's important to note that the data does not need to be in memory from the start of the training, and using PyTorch lighting as a layer on top of PyTorch in order to manage access to GPUs and CPUs, basically also accelerate a lot the development of the models, but also how we standardize how these models are trained and are monitored, and we can manage also, for example, learning rate scheduling and other types of optimization of the training, for example. Similarly, if the models are called with different time series at prediction time, then again this is batched together for the model, which means that you can optimize access time into for example, the GPU in order to accelerate inference as well. Maybe an interesting use case that was tested by our data scientists was on the meta learning part. Meta learning means here in this context is that the model will be trained on a large set of data set. For example, in this case, the 48,000 monthly time series from the M4 data set. And the goal is to see if this model actually performs well on prediction on other types of series. So this was tested on the NBEATS model, for example, and with this 48,000 monthly time series. You can basically just provide the sequence of all these time series to the model, to the fit function. And here what I'm showing is that it's trying to predict on a series that is not that was not in the data set, the air passengers data set. And it does actually quite a good job for default. It wasn't, I think it wasn't even optimized that much for all the series anyway. So the goal here is to see that we get into some form of transfer learning where the signal that was learned on this large set of series was transferred in order to better predict on this new series. And this is a very interesting situation, because then in that sense you can use this model at inference time without having to retrain it. And you, of course, if you optimize also better the model, then probably you get better results. But the idea is that you will avoid to retrain the model every time you have a new time series, and this would accelerate testing a lot and the prediction quite a bit. So another important part of that is support for probabilistic forecasting. So this is coming into many more models. It is supported in all deep learning models. So let's speak a bit about why might we need probabilistic forecasting. So suppose that you have here a time series which is a sine wave time series that was contaminated by adding Gaussian noise to it, and you see here maybe just the intensity of the noise being changing over time as well. So if you take a naive approach to this problem and try to predict maybe with a baseline naive seasonal model, the model will be just copying the value of the time series from one period of one season in the past. So of course, this will be also copying the noise and overfitting the noise. You might take a better approach with ARIMA. ARIMA would also smooth out this noise for you. Let's say here you have picked the ARIMA model that doesn't give you for probabilistic forecast. Here, depending on the noise level, you might be okay because the noise was low, for example, in this spot, or you might be quite off because the noise level was quite high, and then your forecast is quite far from the truth. Ideally, what you would like to have as a forecaster is to get a point prediction, but get also some error bands around it. And this is the goal of probabilistic forecasting. Basically, is to give you this uncertainty around this point forecast that you did. So as I mentioned, all deep learning models support for probabilistic forecasting. And the classical models that have like integrated support also has this support for probabilistic forecasting. So how is it implemented basically in deep learning models? The idea is that you pick a distribution and the model will learn the parameters of this distribution during the training of the model. And the output of a stochastic model is a stochastic time series. Basically, you will still have the dimension of time and the different components that you have in the series, but you add an extra dimension for samples of the time series. So basically, these are different views, let's say, pictures of this time series as different samples from the distribution. So ideally, then you would have this model that will learn these distribution parameters theta, and you get your time series with the different samples of this time series. And from there, you can create your error bands around your predictions in the future. There is a wide support for likelihood functions in darts, depending on the type of data you have. If you have some prior information on your data, if you have some, for example, if you know that your data is discrete, you might use, I don't know, Poisson. If you have if you have some information about your data that you want to integrate, then you can use one of these, like you can use the adapted likelihood function for that. Final word about also some probabilistic reconstruction, since we are speaking about probabilistic stuff. There is support in darts of filtering models, and these models would help you smooth out some noise, but also it can help you fill missing values, for example, inside your data set. There are two classes of this. We have support for Gaussian process filters, which basically wraps around the scikit-learn Gaussian processes, and the Kalman filter, which are, I think, if I'm not mistaken, are an implementation that we have done in darts. So what's up next for darts? I think this is a nice opportunity to call on all of you, if you're interested in developing tools for time series forecasting in an open source library. We are really happy to receive your contributions, but most of all, we would be very happy to have you test the library and give us your feedback. We are always at the lookup of improving the library. And in our improvement steps, we have some big, let's say, big improvements coming along. There is a first shot of anomaly detection tools that is going to come out hopefully very soon. Improvements for regression models to make them faster. More support for static covariates. So static covariates are these covariates that are fixed. They are not, they don't change in time. So unlike the past covariates and future covariates, these are values that are fixed in time. But they could be also very useful in as features for the models. And we are always actually also testing these models, and hopefully at some point we'll be able to provide some good, let's say, advice on how to start with some pre-trained models on hopefully a large series of data that is widely available for the public. So with that, I will take some of your questions. I hope I didn't bore you too much with the details. We have a first question here. I know that trained deep learning models can be saved with my model save path command, but is there any way to save it as H5 or pickle file? Oh, that's a very specific question to be able to answer it now. I will actually invite you to post this question on our GitHub. In my opinion, no, for the moment it's not possible, but I think maybe pickle it's possible. H5, I'm not sure it's possible, but I will maybe ask you to post this question elsewhere. Based on experience, which models are the most effective in time series forecasting? Which models can build the most accurate forecast where the quality of data is not high, lot of outliers? Yeah, I think forecasting is a tricky situation because it's you need to take into account the multiple aspects. For example, you will need to understand if you have some trend in your data, if you have some seasonality first, if you have, like in your case, some outliers. I think it's always good to start with the baseline models. So start with the econometric models and see where this takes you. We have, I mean, I've seen different analysis that was done internally, and linear regression always seems to start very, very well. So start with these models. For outliers specifically, I cannot give you an exact answer now, but think about probabilistic forecasts, and with some larger tails, likelihoods for that. Probably this will cover quite a lot of situations. And a lot of outliers, it could be some anomalies. So maybe check if you can extract them by some anomaly detection algorithm as well. But we always suggest to start really from the baselines, which are the statistical baselines, but also which are simple linear regression to see where this already takes you. Yeah, that should be possible. If I'm not mistaken, it should be in the RNN model or the block RNN model. If you have doubts about that, I invite you also to check on the documentation for DARTs. There should be quite a lot of explanations. Currently, it is possible to, if I'm not mistaken again. GNNs, you mean graph neural networks? For the moment, we don't have support for graph neural networks. So lib looks really nice. As I don't have much experience with time series, if there is any way to combine spatial multivariate time series, that's interesting. For the moment, we're not working on spatial aspects, but there are a lot of commonalities, and like in the let's say in how you treat spatial data, because you can imagine you have similar structures of correlations, because you have closed locations are correlated like in time. And you will have to care about stationarity as well in spatial aspects. For the moment, we don't have support for spatial multivariate time series. But it could be as something interesting, maybe to suggest as an improvement. It's currently not possible in darts itself. I see. Well, for the moment, if you can cast the location as a covariate, then probably you can use it. So, for example, in the not in all deep learning models, and some deep learning models, you can integrate static covariates. This is what I mentioned before. So if you have any information about location is something fixed. It doesn't change with time. Then you can integrate that as a static covariate. We are improving the support actually for static covariates for many of the models we have currently. So you might just need to look at the model that you care about, see if it supports static covariates, and try to encode the location information as a static covariate, for example. This might be a good entry point. Okay, good. I hope you enjoyed this presentation. I thank you very much for your attention. If you'd like to get in touch with us, please do. I am a contributor to Darts, and you can contact me, or you can contact our lead developer and creator of the library, Julien. We'll be always happy to discuss with you improvements of the library, but also suggestions, and we discuss in general time series forecasting problems. With that, I would like to thank you again, and hope to see you in the next edition.